Alright, today I'd like to talk about some basics of computing which are very useful for engineering when we're doing engineering modeling and numerical methods. So who is this guy? Some different options: Wernher von Braun, Max Planck, Kirchhoff, Kalman, Turing, famous scientist mathematicians. It's actually Alan Turing, who's a British computer scientist and cryptographer. Very famous guy in the world of computers, helped us win World War II. I think it's the Imagination Games, a good movie to watch about some of the stuff they did during World War II using computers to break codes. So basic computing does exactly what you want them to do. What you tell them to do. It doesn't always do what you want them to do, it does what you tell them to do. So if you give it garbage instructions, it will give you garbage output. So all of this is based on digital information where everything is just a 0 or a 1, a low or high voltage, and a little piece of electronics inside a computer. So the central processing unit is the brain of the computer, and it basically does simple instructions. At the lowest level, it does stuff like moving information from one memory location to another, or comparing two pieces of memory between this and then doing something. Or specialized where, like for graphics, it processes information and draws things to a screen very effectively, or does sound output and processes different things to make things sound strange or different. So you can do math, graphics, sound processing. Basically, it's all processing information. And you have input and output information. Your input comes in from things like a mouse, keyboard, reading a file, reading a web page. Your output spits out stuff in front of you, like video or sound, file, printout. So all of it is just information processing. Information comes in, it's processed, it does stuff, and goes out to an output, either sound or graphics or a file or printout. So at the lowest level, you usually have a CPU piece of hardware. It has different levels of memory. Some of it has memory that's very quick to the order of operations. Some of it's memory that's on the CPU but not as close. There may be other floating points or other parts of the CPU that do specialized things so that you can get to them very quickly without having to reach too far away to other pieces of hardware outside of the CPU. When you boot up, it has to read the instructions about how things are connected. So a lot of times on a boot screen, you'll see this BIOS, boot instruction operating system. It's very simple, just how things are connected. Then you hook in hard drives, solid state or hard disk drives. You've got RAM, which is memory. So you may have gigabytes of memory these days, whereas on the CPU, there may be just a few hundred megabytes for direct access, but the CPU can grab information from the RAM memory of the hard drive. There may be graphic cards so that you can play in 4K, whatever video game you're playing. There's other stuff you can hook in, like sound chips, network controllers. Sometimes that's on a hard drive. Sometimes it's an actual piece of something you hook in to that system, like either through USB, so you can hook up your keyboard and your mouse. So all of these things have to talk together to get something accomplished. There are different types of hardware. The PCU is not the same. PC CPU is not the same piece of hardware as an old Mac or Unix machines. But these days, PCs have gotten so good. A lot of PCs work the same. A lot of Macs are the same as the PCs and Unix machines. They all use basically the same hardware, and you can install Mac operating systems on a PC if you work really hard at it, and vice versa. But in the old days, there were a lot of different chips. The biggest difference now is between, actually most everything's 64-bit. There's a transition from 32 to 64, but there's big differences between mobile hardware, which is optimized more for less battery usage, versus desktop and laptop usage. So there's differences between the hardware, typically between mobile and PCs, that make it where you can't run Mac operating system directly on some of the hardware. Like the desktop version is different. It's not compatible with the mobile stuff. It's not always true. Microsoft has a Surface hardware that runs real versions of PC on mobile hardware. So it all depends on the stuff, but there can be differences in hardware that limit how you run different things. Like your operating system, your Windows versions, your Unix versions, your Mac, Apple stuff, all these different versions of the operating system that run on the hardware and allow other programs to run inside that operating system. So that operating system is that low-level program that basically shows you how programs execute and components talk to each other. It's the BIOS boot stuff was basically how hardware talks to each other. Operating systems, how programs can do things and touch hardware and do things. What is a program? So you build a program from source code like Excel, Word, PowerPoint, Chrome, whatever, your Internet Explorer. Those are programs you run, and they're built from source code. And source code is just lots of simple blocks, data types, statements, relational operators, less than or equal to, is it equal to, logical operators like and, or, conditional statements like if and then, and loops, for and while loops. So all source code is just made up of simple pieces of one line of information that does something. Define a data type, do a simple statement where you do some math or run a function to figure out something, check something or check something, use if statements and loops to make things happen. And all the specifics on this syntax, how you write these source code, depends on the language. And we have variable names that humans like to know, variable K or variable A, but the computer puts that into some memory location. We don't have to worry about which piece of chunk of memory holds variable K. We assume the operating system and the source code and the programs will figure all that out. So this makes it a little bit more readable by a human, so we don't have to keep track of all the memory locations. So these high-level programming languages do a lot of things for us to make it a lot simpler. There are different types of languages. We have compiled languages like C and Fortran, C++, where you have to write a file and you run it through another program that converts it into an executable that you can run on the hardware. So this means the programs run pretty quickly, but it only runs on the target operating system. It's hard to write a program on a PC and compile it to run on a Mac. You can do it, I think, if you work really hard at it, but in general it's much easier to basically, you get on a PC, you use the compiler to process your source code to make a program. There are other things called interpreted languages. You may be familiar with this in terms of Java or JavaScript. JavaScript and Java programs will run on any browser that is compatible with Java and JavaScript. MATLAB is the one we're going to be using, which if you have a MATLAB program running on your Mac or your PC, you can run MATLAB programs. So it basically looks at what you want to do in the code, and then it figures out how to interpret that and run it in a sort of a protected sandbox, so it doesn't actually need to know much about the hardware or the memory locations. So it's a little slower, but computers have gotten so fast, and some of the software developments has made this interpreted stuff adequate in many cases. So a lot of times, just for engineering's sake, we like to solve problems. How do we get from a starting point to another point? So if we have flowcharts, there's actually symbols that you can use in a flowchart. So an algorithm is a way of solving a problem. It doesn't have to be a computer problem. It could be anything you think of. How are we going to just, I like to talk about order processing. We get orders. How are we going to process these orders from the warehouse to ship stuff out to customers? It doesn't have to be a computer problem. It can just be a flowcharting problem to solve the problem. So our flowchart is a graphical representation. Instead of a bunch of text, it's a way of us visualizing what's going on. And if we're doing input and output for a simple function, it might be in this kind of shape for different types of input, or reading something, or reading a file, or printing something to the screen, or plotting something. This is a single line in an algorithm that you can put together to solve a problem graphically, just represent it graphically. So execution statements are put in simple rectangles. So if you're just changing a variable I, incrementing it by 1 and putting it into the variable I, or adding two variables and putting them in the variable sum, or looking at a vector, a list of values, getting the maximum value and stick it in the variable A, or running some function that you've developed on these two variables and sticking it into variable C. Conditional statements are similar. You come in, at this point you say, I have this variable age, I check it. If this condition is true, I do one thing, otherwise I do something else. And if you put all this together, you could ask, what year were you born? Get the current year, so call some function to figure out the current year. Calculate what the age is. Do something about the age in here with a conditional statement. So you either say you can vote or you cannot vote with the output, and then you stop. So what that might look like in something like a MATLAB code or a more computer syntax is here, where each line is a step in this program. Get the input, calculate something, get the value of the current year, calculate something, and then branch. And notice the indentation here. We have this if statement. It's one if statement, but it's either going to execute this thing or this thing. If this condition is true, this print statement will happen. If this condition is false, this other print statement will happen. The biggest issue about this is tracing the variables. All your variables start with some initial value, and then as the program proceeds, these variables change over time. So here, when we start out, you might have variable A has no value, but then it gets a value when you type something in. And now maybe 2015, whatever the year is, so you can calculate at each step. At the end of the program, these variables have their state, and that is what you're interested in. Does it get to the right state according to the problem you're trying to solve? So you go through each step in the program and figure out what the value, does it change, does it go to something else, does it go back and change over and over? That's what we're talking about when we trace a variable. Pseudocode is just writing code down without worrying about the syntax details. Just basically getting the logic correct. So you may say, get the input data, but this could be lots of steps. It could be a whole program in itself. Check the data. Again, it could be a lot of steps. Then if this, so basically the sketching out the overall high-level approach to solving a problem could be done in pseudocode without having to worry about commas and semicolons and getting everything perfectly right. Now, there's different types of data. We have Boolean data types that represent true and false. In MATLAB, it's 1 is a true and 0 is false. We have integer values that can be positive and negative, and sometimes it's limited to a range. Floating point or scientific notation can be used to represent basically a regular number, a rational number. You have characters and arrays. You can have lists of values. So vectors or primitives, you can stick together characters together to make a string, or a bunch of integers, or a bunch of numbers, or even a bunch of booleans. So there's an array, and even a matrix is an array of arrays where you have a two-dimensional index. And more advanced things are like an object, where you have complex data types put together. So a person might have a first name, which is an array of characters, or string of characters, and they may have an age, and they have an address, they may have lots of different things, but the single variable is just person. And they have these extra pieces of information for that object. So the main ones that we're going to be working with are floating point numbers, true false sometimes, but also arrays. So vectors or arrays, where you have a list of information or maybe a matrix of information. Statements. These statements, each language may have different sets of statements. Min and max may be functions. Floor, if you want to round down. Ceiling, mod, power, sign, exponent, length. There's lots of different functions you can learn about. You can also write your own specialized function. If there's not an average function, you can write your own that takes a vector, goes to the vector, and calculates the average. I think that actually exists as a mean function in MATLAB, but if you want to write your own version that's improved somehow, you could do it. And you could write, if you're doing something over and over and over again, you may want to write your own function to do that on your data. So conditional statements, like I said, you check some condition. If it's met, you do something. Check the value of these two variables. If this value expression is true, do this. Otherwise, don't do this. Please excuse my dear Aunt Sally. It evaluates everything in order of operations. But I like to remember, you don't have to have it perfectly. I start putting in extra parentheses just to make sure if I'm going to evaluate this, and then I want to evaluate this. Over here, I'm going to evaluate this, I'm going to evaluate this, and then put parentheses around everything. Putting extra parentheses in to make sure your logic works is okay in coding, as long as it makes sense. You don't have to be an expert in the, please excuse my dear Aunt Sally, order of operations, and have the minimum set without parentheses, as long as it works to the right logic. Now, two other things other than if statements. We need to know about for loops and while loops. For loops work if you know how many times something should execute. So you have this vector with 7, 8, and 9. You calculate the length. You know there's only 3 elements, so we're going to print out the ith value of x at each iteration. So the first time through, I is going to be 1. So that means x1, which is 7, is going to print out 7. The next time through, I is going to change to 2. x2 is going to be the 8, so it's going to be print out a value of 8. And then the third time through, I has a value of 3. So the third element of x gets printed out. So you get 7, then 8, then 9. So this for loop might look something like this, where you set up this value in x, stick these 3 values into an array or a vector in x, calculate the length of x and put it into A, set up the initial value for I, print the first value of x, increment I, and then have basically this for loop. You can do it with this if then else. If I is less than A, yes, go back here and just do this loop over and over and over again. So here's a more complicated one, for loop. It's basically the same, but now every time you go through the loop, you do 2 things. You print the value of I, and you print this value, grab the value from this vector, the ith value of that vector and multiply it by itself. So the first time through, you're going to do two things. Print out I, which is 1, and 7 times 7, which is 49. So then I goes to 2, you're going to print out 2, and the second value of this vector, 8 times 8, 64. The third time through, you're going to print out 3, and the third value of this vector, 9 times 9, 81. While loops, if you don't know how many times it's going to go, you can use this until it converges or until you break out of it. But if you're not careful, it can go forever and never stop. So in this case, I equals 1, you start with, while this input equal a number greater than 100, you can basically keep doubling the value of I until it exceeds 100. So this might be the code that you write. It's like basically a for loop. Set up some values, run a while loop. This is the start of the while loop. This is the end of the while loop. And it goes through over and over and over and over and over. So it says set up A equals 0, get a number, you go in. If I is less than A, we're going to say, let's see, where is it? If I is less than A, it's going to check this value. I don't think this is a good example. Maybe we should skip this one. So, like I said, you can do multiple things inside a for loop, multiple things inside a while loop, or an if statement. And you can do things like an if statement inside an if statement, or a for loop inside a for loop. So, looking at this code, what happens after we run this section of code? X equals 6. If x is greater than 2, do this otherwise. But we said x is equal to 6, so is 6 greater than 2? Yes. We're going to do this, and we're going to change x to 4 times x, so it should be 24. For this one, we have start off and we say x is nothing, and then we're going to go, j is going to count from 1 to 3. So j is going to be 1, 2, and 3. The first time through, it's going to set the first value of x to 10 plus j, which is 11. The second time, it's going to set the second value of x to 10 plus 2, which is 12. And the third time through, j is going to be a value 3, so it's going to set the x3 value of x to 10 plus 3. So it sounds like it's going to be an array, 11, 12, and 13. This time we have a sum. We start at 0, and we set x to be this vector of 4 values. We get a for loop that's going to start with j equals 1, and it's going to go to the length of x. Well, the length of x is 4, so it's really saying j is going to go from 1 to 4. So sum started out with 0. The first time through, we're going to say 0 plus x1, because j is 1. So that means 0 plus 4 is 4. So sum is 4. The next time through, j is 2. And sum is 4. So we're going to say 4 plus the second value of x, 4 plus 3, so that's going to be 7. So sum's going to go to 7. So the third time through, sum is 7, and x3, j is 3 now. 7 plus 5 is 12, and 12 plus 2 is 14, so it should end up with the variable sum being 14. You can have if statements inside of if statements. So basically here you have an if statement. This if statement matches with this else and this end. If this is true, then you can execute this if statement inside the part that's true. But if this is false, this if statement will never, never happen. So if a is less than or equal to 0, you're going to do this down here. And again, you can represent logic with flowcharts to go through a process trying to solve a problem. So going through this step where you come in and you go this way or this way. It gets to be complex for complicated systems. Some people are very graphically visual instead of reading text, and that's one reason sometimes we try and think through these process and flowcharts, because sometimes some people's minds think like this, where you go through flowing through information, make sure you can get to different places. But eventually we have to convert everything into code that looks like this. You can have a nested for loop, especially if you have a matrix of values with rows and columns. So you're going to go through every row and every column. So the first row, you're going to have row 1 and 2, and then when row is 1, column is going to go through 1, 2, 3. So column 1, 2, 3. And then after these are done, after the inner loop is done, you say, okay, I'm done with row being 1. I'm going to go back and say row to 2. So row goes to 2, and the inner loop starts executing. Column goes to 1, 2, 3. So row is 2, column goes to 1, 2, 3. It's saying the row and column values of this X matrix now to be row times column. So 1, 2, 3, and 2, 4, 6. So you end up with a 2 by 3 matrix of values. So if we have this, y equals 3. If y is greater than 0, we're going to do this, or otherwise. So if y is equal to 3, it's greater than 0, that's true. If y is greater than 2, which is true, we're going to say y equals y plus 1. So 3 equals 3 plus 1, which is 4, which I think is right. And none of these other statements don't execute because this was true and this was true. This is the only statement that executes. This is only happening if this is true and this is false, and this is only happening if this is false. For this one, we have a for loop that's going to go through 4 times, and k is going to go through 3 times. So the row index is going to go through 4 times, and the k index is going to go through 3 times. So it's going to be a 2-dimensional array or matrix with 4 rows and 3 columns. So it's a 4 by 3 2-dimensional array. You can always define your own subroutines if you want to, and there are ways to do that here, going through this problem. There's ways to do that in MATLAB where you take input and you figure out some output. And one of my examples I like to talk about is the bisection method. So you start out with a variable x, and if you're trying to find the value for f of x equals 0, that means you have some function and you start off with lower bounds and upper bounds. If you assume that you have a continuous function and you have at the lower bound and the upper bound positive and a negative value for the function, you know there's a 0 crossing. It could be multiple 0 crossings, but at least with this bisection method, you have to have a positive and a negative, or a negative and a positive, so that there's at least one crossing of this continuous function between xl and xu. So this is a nice one to try and execute. Start off with this is just pseudocode, so it's not exact code. Start off with xl and xu, determine the midpoint, find the function values of the lower, the upper, and the midpoint, and then a while statement. While the midpoint function value, which you want to be close to 0, is greater than epsilon. You want to drive this midpoint function value close to 0. And we square that because if epsilon is our limit, if this is a small number and you square it, it's still going to be positive. So it simplifies some of the logic there. If these are both, fxl and xm are both positive, we set xl to xm. Otherwise, we move xu to xm. Then we have to determine the new midpoint and the function at that point. So basically, we're going to evaluate this and keep moving things around. If you want to be more advanced, you put in error checking to make sure that you start off and your initial values were valid. So a little bit of extra code to make sure the program works a little better. And when you're debugging, you may want to go through and add print statements to figure out. So basically, you're going to make errors. Try and think through the process step by step like a computer. Visualize what's happening in each variable, each step. Add some print statements to print out values as the program runs. Get something working as you expect and then expand it to do more. Try small cases instead of going through all of your data, just try the first couple of pieces and see if it works. Variable names depend on language, what you can name things. I is usually a nice counter, but it's pretty short. Instead of using first loop integer counter and having to deal with that long word, or some people use this capitalized mix of capitals and lowercase without underscores. Whatever works for you, really. But personally, I think I have to deal with upper and lowercase variable or characters and variable names. Put comments in so you can figure out what you're doing, and then think about what cases may break things if you run into them. All right, and that's about it for this.